Okay, so last week we proved a theorem, which was our first incompleteness theorem. That's the theorem in the form we proved it was this. That every consistent computably axiomatized extension of a certain axiomatic theory of arithmetic, which we call Q, well, which people call Q. So computably axiomatized extension of this very basic axiom system Q is incomplete, in the sense of being an incomplete theory. So there is some sentence in the theory, there is some sentence in the language that is neither in the theory, that's a consequence of the axioms, and nor is its negation in the theory either. So its negation is also not a consequence of the axioms. I'm just trying to find a red pen because I always like drawing red boxes around important theorems, but there is no red pen, so we'll have an orange box instead. And I also remarked that, so the notion of one consistency was a notion we came across for the first time last week. It just meant, one consistent just meant if a sigma 1 sentence belongs to the theory, then it's true. So for existential properties, the theory does not prove any false existential properties. But I did remark that with a bit more work, one consistency can be weakened to just consistency. So, and this will be done in the exercise class, I think, next week. So with more work, I'm not going to address this in the lectures, so with more work, one consistency can be weakened. The assumption of one consistency can be weakened just to the assumption of consistency. The assumption of consistency is necessary because the inconsistent theory is trivially complete in an uninteresting way. So this theory Q, it had 7 axioms. So it was a finitely axiomatized theory. It doesn't try to be a complete theory. There's loads of stuff you can't prove in Q, and those of you who went to the exercise class yesterday will have seen lots of things you can't prove in Q. The theory that people like as the canonically axiomatized theory of arithmetic is arithmetic, where you add the induction axioms. You can also weaken the induction axioms to only apply to certain classes of formulas. So one of those is I sigma 1, and that's going to be very important in next week's lecture, when we do Gödel's second incompleteness theorem. Sitting between I sigma 1 and Q is I delta 0, where you only have induction for formulas that involve only bounded quantifiers. I think that might have played a role in the exercise class yesterday, did it? I think most of the things you do in the exercise class could be proved in I delta 0. But all these are computably axiomatized theories. They're all one consistent because the axioms are all true. So anything you can prove is true, not just existential statements. So they're all incomplete. So they are far away from, here we have the theory of the natural numbers, which is the theory of true arithmetic, and we're trying to axiomatize mathematical proof and get as close as possible to here. But because this theory is so general, no matter what axioms we add, as long as we can computably describe the axioms, so we can tell whether we have an algorithm to tell us whether a sentence is an axiom or not. If we're in that situation, we will be, the conditions for this theorem will apply, and we will be in, we will have an incomplete theory. So we are back, axiomatizations are guaranteed to omit some truths. Okay, so today what we're going to do is we're going to prove the same theorem again. But we're going to do that because, well, for a number of reasons. The first one is that last week's proof of this theorem was not really self-contained, so we borrowed a big result from computability theory. So I won't write it down. Anyway, last week we were using computability theory, and today what I want to do is follow Gödel's original. Well, he did not prove something of this generality. He proved a specific theory that's similar to Vienna arithmetic, that was actually taken from Russell's Principia Mathematica. He proved that a specific theory is incomplete, but his methods basically apply in this generality. So today we're going to prove the same theorem, Gödel's first incompleteness theorem, using Gödel's methods. So the title of the lecture is Gödel's first incompleteness theorem. And so we're going to follow basically his original approach, and there are several advantages for doing it this way. So advantages of Gödel's approach compared with what we did last week. Well, one, it's more self-contained than what we did last week, so we're not going to borrow a big result from computability theory. Interesting. And in particular, the way it works is based on finding a clever sentence that turns out to be a sentence that's neither it nor its negation is provable. In fact, we're going to find a clever true sentence that is not provable. And in order to find this true sentence, the sentence is going to involve the property, the characteristic of being self-referential. It kind of refers to itself in a way. So it's kind of curious how you can do that in the first place, based on the concept of self-reference. So when I was a teenager, a book which is now very well known, which is obviously quite an old book by now, called Gödel, Escher, Bach, was published. And that whole book, the Gödel, well, Gödel is one of the three people in the title, but a main part of that book is actually giving a proof of Gödel's incompleteness theorem aimed at a not particularly mathematical audience. But another feature of the book is that, inspired by the works of Gödel, the mathematician, Escher, the artist, and Bach, the composer, Douglas Hofstadter, who was the author of the book, tried to make a big philosophical theme out of the notion of self-referentiality. And in fact, he's published subsequent books in which he's expounded on this further, and he sort of believes that self-referentiality, the ability to understand self-referentiality, is kind of crucial to consciousness, or something something like that. Anyway, I don't want to paraphrase his ideas, but yeah, this concept of self-reference provides food for thought, and there is some interesting literature in which that food for thought is tasted, I suppose, or had. I don't know what the right metaphor is. And the other really important advantage, so maybe a better advantage from our purposes, is that Gödel's approach leads to further developments. And these further developments are mathematically and philosophically interesting in their own right. So it leads to further developments about the nature of incompleteness, and one such further development is what's called Gödel's second incompleteness theorem, which is going to be the topic of next week's lecture. So we can't do Gödel's second incompleteness theorem without doing what we're going to do today. Another difference with last week is that today we're going to come up with an explicit sentence that is true but unprovable. Last week we did not have such a sentence, but I don't want to put that down as a difference between the approaches, because actually if we'd worked a bit harder on last week's theorem, we could have also come up with an explicit sentence using the methods last week. But we would have had to have worked quite a bit harder, and in doing so done half the work that we're going to do today as well in order to get that explicit sentence. Okay. It's going to be more self-contained, but there is no avoiding some computability theory, in the sense that, so we're no longer going to need a big result from computability theory, the existence of a semi-decidable but not decidable relation, which is what we used last week. But nonetheless, we still cannot avoid dealing with computability theoretic concepts. For example, the very statement of the theorem is about computably axiomatized theories of arithmetic. And so we're going to need to have some formal mathematical handle on what that means. So far, the notion of computability has been a little bit informal, the existence of an informal algorithm that will give us a decision procedure. So this course does not assume computability theory, and there's actually a very nice way around it that we have available, which is, because we have the logical language, we can define the computability theory concepts we need using the logical language. So we can define them as logical properties. So I'm going to begin the lecture by doing that. So we already discussed, I think it was the lecture on decidability via model theory. We discussed informally what decidability means and semi-decidability. So we're now going to need to have formal definitions of these. And I'm going to take as my basic context for this the semi-decidability or decidability of relations on natural numbers. So K-array, K-argument relations on natural numbers. So we're going to say a relation, so it's a K-array relation, so if we view it as a subset of n to the K, is semi-decidable, or in standard mathematical parlance, computably enumerable. So there are I'm only going to write one, but in the notes for the lecture there are three equivalents. computably enumerable, semi-decidable, and recursively enumerable. They're all words for the same thing. We're going to say the relation is computably enumerable simply if it is sigma 1 representable. Okay, so we had this notion last week. Sigma 1 representable if there's a formula with k free variables, if there's a sigma 1 formula with k free variables, such that the k tuple is in the relation if and only if that formula is true when instantiated with the numerals for that k tuple of numbers. Okay, this was a definition last week. I'm not going to repeat it, apart from I just said it. So how does that relate to the informal notion of semi-decidability? Well, semi-decidability is given a k tuple as input, we should have some algorithm which will, if the k tuple belongs to the relation, will recognize that it does so and will eventually hold. And if we have a sigma 1 formula representing the k tuple, well, the sigma 1 formula is some existential quantifications followed by a delta 0 formula. So we just have to guess the numbers for the existential quantifiers and then check that the delta 0 formula holds. And the delta 0 formula, because all the quantifiers are bounded, we can decide, or we can decide even in polynomial time, given the numbers, we can decide whether or not that property holds for that particular choice of numbers for the existential quantifiers. So we simply have to guess the right instantiations for the existential quantifiers, or alternatively, we can search through every possible k tuple of numbers until we find one such k tuple. Sorry, not k tuple. Sorry, we search through all possible tuples of numbers that give us numbers for the existential quantifiers until we find one for which the delta 0 formula holds, and then we stop. And that's our semi-decision procedure. And then there's the notion of decidable. So we say that a relation is decidable or computable or recursive. Again, I'm just going to write one of the words here in the lecture, and the others are written in the notes. Well, we had the informal notion of decidability in the previous lecture on decidability via model theory, and we proved an informal theorem that a set is decidable if and only if it and its complement are semi-decidable. And we're just simply going to take that as the definition of decidable. Because it's an easy definition we can make because we've got the notion of semi-decidable already, which is computable enumerability, which we're defining to be sigma 1 representability. So R is computable if both R and R complement are, so I write RC for the complement relation, are computably enumerable, which is abbreviated CE.
Excuse me.
Yeah.
Does it hold that a relation is sigma 1 representable if and only if? Okay. Does it hold that a relation is delta 0 representable if and only if the relation and its complement are sigma 1 representable?
So the question is, so if a relation is delta 0 representable, then it and its complement are both sigma 1 representable, so it is indeed computable. But there are relations that are computable that are not delta 0 representable. In fact, all delta 0 representable relations are quite efficiently computable. I mean, there's some polynomial time result you can get for them. Those are exactly what it is. So lastly, we also have the notion a primitive recursive function that was introduced in the exercise class a couple of weeks ago. Primitive recursive functions are a special class of computable functions that have this very nice inductive mathematical definition. The notion of primitive recursive function also gives us the notion of primitive recursive relation. So we say that a relation n to the k is primitive recursive. Maybe this was also in the exercise class, I don't know. If its characteristic function is a primitive recursive function. So if the function, I'll write like this, chi sub r, the characteristic function, so this goes from n to the k to n, but it's only going to take values of 0 and 1, or the indicator function is another word for it. So if this is primitive recursive as a function, as defined in the exercise classes. So the characteristic function, just to be explicit, defined applied to n1, nk, is defined to be 1 if n1, nk are in the relation R, and 0 otherwise. Three main concepts we need for relations. We've got semi-decidable, which we call computably enumerable, decidable, which we call computable, and what is in fact a stronger property than decidable, primitive recursive. And indeed, it's a stronger property because we have the implications if R is primitive recursive, well, let's leave R out, but anyway, just anonymously, if you're primitive recursive, then you're computable, and if you're computable, then you're computably enumerable. So this is a proposition, if you like, but I'm not going to bother to name it as such. Chain of two implications. The second implication is immediate from the definition of computability. The first one, this holds because we've got the tricky result that's involved Gödel's beta lemma, where we proved the representability, the sigma 1 representability of exponentiation. I told you at the time that that could be naturally generalized to arbitrary primitive recursive functions. So every primitive recursive function, its graph is sigma 1 representable, which means that primitive recursive relations, their graphs are sigma 1 representable. And together the complement is sigma 1 representable. Well, it's actually easy to show that, so if the characteristic function is primitive recursive, then so is the variant where you swap 1 and 0. It's also primitive recursive, and hence, the graph of that function is also sigma 1 representable, hence the complement of the relation is also sigma 1 representable. Okay, right, so this is easy stuff. There's one other tricky fact we need, which in the notes is at this point, but maybe I'm going to break things up a bit. I'm going to go on a bit now with the story for Gödel's theorem, and then bring in this other result at the point we need it. But there's one more result to do with these sorts of things that we're going to need later. As I say, let's skip it for now, and we'll move on to Gödel's approach to his theorem. So Gödel's approach to incompleteness. So we're going to work with a computably axiomatized theory. Okay. And let's see what I want to say. So, so we work with a computably axiomatized theory T. Yeah, by the way, so we had the notion of, we've got the notion of computably axiomatizable theory. And I'm going to try to be quite careful to distinguish between computably axiomatized and computably axiomatizable. So computably axiomatizable means we have a theory and it has some computable axiomatization, but perhaps we don't know what it is. By computably axiomatized theory, I mean we have a theory with a computable axiomatization, and but we're considering it as given with a particular given computable axiomatization. So that's always going to be the case if we're working with an axiomatization, because we'll have a set of axioms. And we're going to show that various properties, so the crucial idea is what's called arithmetization, and it's to show that important properties of T can be encoded as number theoretical statements. So we show that properties of T, such as formula A is provable in T. Or more briefly, we would write that as using this notation, using the provability turnstile, can be encoded as number theoretic statements, but not just in informal number theory, but actually number theoretic statements formalized in the language of arithmetic. So we show that these can be encoded in the language of arithmetic, LA, as we call it. And so for this purpose, Gödel introduced what's subsequent to his paper being called Gödel numbering. Gödel numbering means systematic numbering of everything we need in order to turn such statements into statements about numbers. So we need to number the syntax of the syntax of the language, so number all terms and all formulas, and also number the proofs, and be able to check properties like is something that looks like a potential proof really a proof of the sentence from the axioms and this kind of thing. Okay, so we need to look at Gödel numbering, and probably many of you have seen similar things before. It's not nowadays that we're used to doing everything on a computer. We're used to the fact that basically all the work we do, and we can certainly include logic in the work we do, especially if we use proof assessments and things like that, but all the work we do ultimately has to be input into a computer, so what ultimately has to be converted to numbers, moreover in binary representation. So it's not surprising that we can do this, and you know, basically the task is to try and do it in as painless a way as possible. So we're going to do a Gödel numbering of our language. Now, if we're writing down formulas, we would tend to basically just write them as a sequence of symbols, perhaps with some brackets in, if we wanted to, in order to disambiguate things. We might force the use of brackets. or if we were very meticulous, we might insist on some sort of reverse Polish notation or something like that and not use the brackets at all, which would actually simplify the numbering, but not simplify the readability of what we're doing. I'm not going to do that. So I'm just going to basically write formulas as sequences of symbols and require us to be able to parse them. If you've done some computer science, you might know something about parsing. So we're going to use sequences of symbols, and I'll use S to stand for a symbol. And actually, we don't have very many symbols. We don't need that many symbols because we can restrict ourselves to a sufficient set of logical connectives, in which case So in the proof system, the Hilbert proof system, I just had bottom implication for all. That's the only logical connectives. We have equals as the only relation symbol. Then brackets might be useful, so we'll have open and closed brackets. We've got the various function symbols from the signature. So that's 0, successor, plus, and multiplication. At all that we need in the language are variables. So we'll simply just give ourselves a countable collection of variables. Now, when I've been writing formulas, I've been using X and Y as meta variables, standing for actual variables. We don't normally bother to look at actual variables. But now we're going to need them because we're encoding a concrete syntax. So we're simply going to call our variables V0, V1, V2, V3, and so on. And we've got infinitely many of them. And I'm going to give each symbol a number. So I'm simply going to call its number hash S, hash for the number of S. And I'm simply going to number them starting with 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, excuse me, 10. Anyway, you get the idea. But if that's consistent with what's in the notes, yep, does seem to be, almost. Okay, so, and then a term and a formula will be a string of symbols. Not every string of symbols will be a legitimate term or a legitimate formula, but that's a parsing job to find out which ones are correct terms or formulas. So a string of symbols we're going to call, so a string or a sequence or a word of symbols. We're going to use the notation, for some reason I'm starting counting from 1, so if we've got a word of length n, of n symbols, we're going to code this as, so here I use corner brackets to mean the code, that's called the Gödel number of this string of symbols. And because we have exponentiation definable in the language of arithmetic, we can use exponentiation if we want to actually encode. Well, I'm jumping ahead a bit at the moment. I mean, for now we're just defining this. This is a numerical value. We don't need to bother worrying about how to actually calculate that value in the language of arithmetic. So I'm simply going to use the simple approach to coding sequences, where we use these numbers as powers of the prime factors of a composite number that represents the whole. Well, in general, or probably in most cases, if it's got more than 2 distinct symbols, it'd be a composite number. So we can encode the sequence 2 to the power of the code for S1, 3 to the power of the code for S2, and so on, all the way to the nth prime. Hang on. The nth prime. Yeah, that's right. The nth prime to the power of the code for Sn. So to find the ith symbol in a sequence, you simply calculate the prime factorization. It's not particularly efficient, but anyway, you calculate the prime factorization and you extract the ith prime in the prime factorization and you look at its exponent. So, that's
so in the meta theory, we need a pretty hefty proof that natural numbers are uniquely decomposable to this product of the power of primes.
Well, we need a proof of the is it called the fundamental theorem of arithmetic?
Yeah,
indeed. You can decide for yourself whether that's a hefty proof or not. Okay. So in the notes there are some examples worked out, but does anyone want to see some examples written down? No. Yeah, if there was a chance you needed to actively be enthusiastic about it for me to feel persuaded to do that. So now let's consider some properties we want to state of numbers that will recognize will say this number represents something syntactic that we're interested in. So let's consider some so consider the following relations on numbers. Relations including unary predicates. So the first one I'm going to call term of n, and this is defined to hold if and only if there exists a term in the language such that n is the code for the sequence of symbols that represents that term. Okay. Exists a term T in the language of arithmetic such that n is the numerical code for the sequence of symbols in the term T. I already mentioned, maybe if one wanted to avoid brackets, one could use reverse Polish notation. Actually, another alternative would be to use syntax trees instead. And that's also a sort of be a nice way of doing things, except it's more complicated to explain. With the way we've got using sequences of symbols, the difficulty gets pushed into, so we now have a well-defined property of natural numbers. It actually turns out that this is a primitive recursive relation. Now that's not totally obvious. It's primitive recursive because you can write a program that given a sequence, given a number that we take off as encoding a sequence, decomposes it into the components and parses it to see if it's a term. And then, if the parsing succeeds, then it says then this primitive recursive function returns 1, and if the parsing doesn't succeed, it returns 0. It's not totally obvious one can do that in a primitive recursive way, but one can, and I'm not going to elaborate on that further. But 2 weeks ago in the exercise class, you did go some way to seeing the power of primitive recursive, after primitive 2 or 3 weeks ago, whatever it was, the potential power of primitive recursive definitions. Okay, a similar parsing problem, but slightly more complicated because it also has to deal with variable binders, like for all that exist, is the relation formula n, which has basically a very similar definition. There exists a formula A such that n is the code of A. And a related predicate is that there exists a sentence A. So it's a special case. Basically builds on the formula, it checks that we've got a formula, and then it goes and checks that there aren't any free variables in the formula. So sentence says there exists a sentence A. Lastly, what's going to be a really important function for us is the substitution function. So I'll call this sub. And the substitution function is going to have 4 arguments. And this holds if and only if there exist a formula A such that X is the code for A, a term T such that Y is the code for T, a variable, all our variables are of the form VI for some I, such that Z is the number of VI, list all those such that W is the code for the formula A with the variable VI replaced by the term T. Okay.
Excuse me. So we're not considering VI as a string.
No, because it's always a variable in this position, so we might as well just use the we might as well just use the code for the variable. If you wanted to, you could. Yeah. Okay, and the fact all these, so I already mentioned it for term, all these relations are primitive recursive. Rautenberg. So Rautenberg book does the material that we're doing today and last week very thoroughly and very well. I don't know to what extent this is justified. This is the kind of thing that it's hard to find many details of in the literature, probably, but I don't know to what extent it's covered in Rautenberg. But I'm not sure how many details one would really want to see. These kind of things. Yeah.
So you said that this is kind of almost non-existent in the literature.
Well, maybe, yeah. Yeah.
Well, I can see why, because it's very tedious. But do all the people relying on this result just believe really hard in their heart that it's true? So seems kind of. I would like to see it really justified at least in one place. So.
Okay, well, please do a search, and well, people have formalized Gödel's theorem in proof of systems. So probably somewhere like that, these things are all justified. I don't know what approaches they they follow. I mean, certainly when I was learning this material back in the day, I felt like I sweated hard enough with primitive recursive definitions that I was 100% confident about this, and I kind of put all the details into a place in my memory where painful things go that I don't want to sort of reopen. And but you're very welcome to, you know, if you doubt this at all, you're very welcome to try and find it in the literature and think about it yourself. I'm not going to go further into this. Good. Any other questions? Right, well, it seems to be break time, so yeah, start again at 15:15. Okay, so what we've done so far is we've encoded syntax as numbers, done Gödel numbering of syntax, of terms and formulas, and of an important operation on syntax, namely the substitution operation that substitutes a term for a variable in a formula. We need to go beyond this to address the theorem as a whole and show how to encode proofs and provability. Now, the ideas for that are sort of natural progression from where we are, so it's not going to be very difficult, really any more difficult to do that. But still, I'm going to postpone that because with just this machinery, namely the machinery for encoding syntax, we can already state and prove that what is really the key lemma in Gödel's first incompleteness theorem, which is where the lemma in which the essence of self-reference lies. And this is called Gödel's diagonal lemma. So let's write that down. It has a very curious statement. But let A be any formula in the language of arithmetic, so any property of numbers. So it's actually going to have one free variable, so it's stating a property of numbers. So for any formula A with one free variable, and because we've got a specific collection of variables, v0, v1, v2, let's just make the variable v0. So for any formula, there exists a sentence B such that it's provable in Q, this weak theory, that B holds if and only if A holds, where instead of the variable v0, we substitute the numeral for the Gödel number of B. So that looks extremely weird, but you understand it, one understands it as follows. So A is stating a property of numbers, the numbers that we use to instantiate v0. We're going to understand A as stating a property of sentences under their Gödel numberings. Of course, A may hold for some formulas that are not, for some numbers that are not the encoding of sentences, but never mind, we're kind of understanding A as expressing a property of sentences. And understanding it in that way, it says for any property whatsoever that's expressible in the first order language, there exists some sentence B that says of itself, A holds for me. Okay? So B is true if and only if A holds for B. Where we're understanding A as expressing a property of sentences via their Gödel numbers, and we have to put the numeral in here just to make it a term to substitute into the form. Okay. So that's the statement. For any property, which we think of as the sentences, there's a sentence that says A holds of me. It might be false, it might be true, but it's equivalent to A holding of it. So it's saying A holds for me. Okay, so I'm going to give the proof of this. I always find this proof very unintuitive and hard to follow. It's very closely related to proofs like Cantor's proof, diagonalization proof that every set has cardinals strictly smaller than its power set, for example. Another similar proofs by diagonalizability. And there's in fact a nice little category theoretic fixed point theorem called Lorbe's fixed point theorem or fixed point lemma. But this can be viewed as an instance of, and also Cantor's theorem can be viewed as an instance of. Nonetheless, when we actually do the details of this, I find it hard to explain it in some intuitive diagonalization terms. So I'm sorry about that. That's probably my failing. So I'm just going to give you an argument that one can follow from start to finish bit by the logical steps going, but I'm not going to provide very much insight for it. So we're given A0, so we're given a formula A, which has one free variable B0. Now, we need, for this proof to work, we need to use a variant of the substitution function. So I'm going to define that. That's why I left this material on the board, because I want to compare this. We're going to give another substitution function on three-place relation, and I'm going to call it sub-num, meaning substitute a numeral. So this takes three arguments, M, N, and L, and it's defined to hold if and only if M equals the code of some formula D, and in which case L is required to be the code for D with the numeral for N substituted for the variable V0. So and L is the code for D with the numeral for N substituted for the variable V0. I mean, D may not contain the variable V0, but in that case, the substitution doesn't do anything. Okay, so we substitute the numeral of N for free occurrences of the variable V0. And once again, this relation is primitive recursive. Again, primitive recursive. Okay. So, because it's primitive recursive, it's represented by a sigma 1 formula. So the sub-num is represented by a sigma 1 formula, which I shall also call sub-num. have variables of v0, v1, and v2, but I'm just saying it's a three-place, it's a formula with three variables in, so these are meta variables. That's completely fine. Okay, and now we're going to use this representing formula and do some clever stuff. But before saying how we do that, there's one other thing I need to add here, that actually it's not enough that this is just represented by a sigma 1 formula. We need a slightly stronger property of the representability, which I'm going to call strongly represented. That property is until after we've proved the lemma. And this was the thing I postponed from earlier. Okay, there's a strong representability of primitive recursive relations. We'll see what we need at the end of the lemma. A formula that strongly represents, but for the moment we'll just think of it as represents the subnum relation. And we consider the formula which I'll call C, which only has one free variable v0, which is defined as follows. It says there exists a v1, so now I'm going to be careful about the names of variables. There exists a v1 such that subnum of v0, v0, v1, and A holds for v1. So that looks completely puzzling, but we can make some sense of it by considering what C says if we plug in the code for a sentence D as v0. So for any sentence D, it says formula in my notes, but I'm pretty sure it needs to be a sentence. I'm pretty sure we only need to consider sentences. So for any sentence, I'll backtrack on that if we need to. So for any sentence D, we have that C holds for the code of D. And again, we put the numeral in. In the notes, I don't have all the numerals written in because we got bored with writing them, but let's put them in for the sake of the lecture, just to be meticulous. So C with D substituted, this says that there exists a v1 such that subnum of these, okay, so subnum of D, the v1 and a v1. Now, because subnum is basically a function, this is saying that A holds for the formula D with the new we don't want a sentence. Allow ourselves to substitute the variable v0. So sorry, I was completely wrong about wanting a sentence here. Okay, so C of D says for the formula D, if we substitute its own code for the variable v0, A holds for that substituted. A holds for the code of that substituted formula. Then we know that this relation is a partial function. Given m and n, there's at most one L that satisfies it, which is this substitution, and it satisfies it under the condition that D is the code of the formula. So in fact, the only possible value we can have in the right-hand argument there is D with its own code substituted for V0, because we need the code of that. Okay. The notation is getting pretty horrible, but all right. And because Q said, because C of D says this, we can actually prove in Q that C of D holds if and only if. So this is the only value for V1 that satisfies the subnum relation. And C of D says that A holds for that value. So this is not too surprising that this holds if and only if A holds for this. So D with the code for D substituted for D0. The code for that. Okay. Now, one direction, the left to right direction is clear, because if C, no, hang on, sorry, CD is this formula here. So the right to left implication here is clear, and it's clearly provable in Q, because here we've got a witness, and we're just showing that the existential property holds, because this is true, and this is provable in Q because it's by the sigma 1 completeness of Q. The other implication says that if this holds, then A holds for the number that we know is the unique value that's in the subnum relation here. It actually requires a bit of power for Q to be able to prove that this existential property that holds for a single number really does imply that the Q knows that that's the only number, essentially, for which the property A holds. And this left to right implication needs a stronger representability property. And this is, so here, the left to right implication requires strong representability, which will come to what that means. After we've completed the proof of this one. Okay, but we're now nearly done. Can anyone see how we wrap things up? It's asking a lot while I clear the board. Maybe we'll continue on the bottom half of. We simply say take C to be the formula D. This is like all these diagonalization proofs work like this, that you consider some property that substitutes something inside itself or does something similar, and then you instantiate the well, anyway, you will, if you think about other proofs like Cantor's proof of the greater cardinality of power sets, you'll see an analogy here. So we now take C to be D. So I'm continuing the proof here, taking C to be D. We have that hang on, do we have a formula D? No, we've got a formula C. What am I saying? We take D to be C because we have a formula C. D was just an assumed form. Taking D to be C, we have the Q proves C. I'm going to stop putting the numeral bars in. C with C substituted for the V0 holds if and only if A holds for C zero. But here this notation means V0 was the only variable, and by this I meant the substitution of that variable with the numeral for C. So all the quoted numbers should be numerals. So this is the same as this. E is the formula. Find B to be the formula C with its own numeral substituted, its own Gödel number substituted for V0. Yeah, I mean, maybe let's put the numeral bars back in just to be. Okay, and we're done. So a clever little proof, and it does what it's required to do. Okay, so the remaining thing to show, to expound upon, so it's not too unintuitive that this holds, but I still need to tell you what the notion of strong Q representability is to be complete. Are there any questions on this, by the way? I remember the first time I saw this, I was kind of very unhappy with the use of a particular variable name and this sort of thing, but it really seems it's the best way to do it. So, to justify I've used this notion of strong representability, so we need to justify that. So for this we need a lemma. We'll call it strong Q representability. This says, suppose we have a computable relation, R, so that's decidable, is computable, and moreover, it's a partial function. So for any k numbers for the x's, there's at most one value for the y that satisfies, that's in the relation with those. So for all n1 to nk, there is at most one n such that n1 to nk and m are in the relation. And that was satisfied by the subnum relation because it was substituting a numeral in the second argument for a variable in the first place, and then there's in the cases that the first two arguments were indeed codes of the first argument was a code of a formula, then the third argument, the value in the third argument was determined because it had to be a certain substitution. So then we have a sigma 1, then R is representable by a sigma 1 formula that doesn't just represent the graph of the relation, but also satisfies a further property. So then there exists a sigma 1 formula, AR, let's call it, with the right number of free variables, so x1 to x, k, we've got k variables, and y. Computability said that this formula is true for a k plus 1 tuple of numerals if and only if that k plus 1 tuple of numerals is in the relation. We're going to require something stronger than that. So in the one direction, we require that if a k plus 1 tuple is in the relation, sorry, if the formula is true for a k plus 1 tuple of numerals, then they're in the relation. But I'm going to state that in a different way because just to make some symmetry here, I'm going to use provability in Q rather than talking about the semantic relation of the formula being true for certain numbers. Because by sigma 1 completeness and 1 consistency of Q is equivalent, but I'm going to talk here about, so this says if the formula is true for numerals n1 to nk and m, but as I say, by 1 completeness and 1 consistency of Q, this is just the same thing as saying the formula is true for those numbers. But in the case that that holds, we require that indeed n1 to nk and m are in the relation. But the other implication is going to be stronger than the converse to this. So the other implication is that if a k plus 1 tuple of numbers, m1 to nk and m, are in the relation, then Q proves that not just this formula, but it proves that m is the only value that satisfies this formula. So in other words, it proves for all y, that's an unbounded universal quantifier. The formula AR holds for the tuple m1 to nk and y, if and only if y is equal to m. That's the stronger property that we were using. Well, I've rubbed off the place that it is used, but we were using in the highlighted implication of the in the proof of the diagonal lemma. That you should look at the Rautenberg book if you want to see more details about results in for example the results on Q that we did last week. So actually my presentation here differs a little bit from Rautenberg's in the sense that last week I defined the notion of sigma 1 representability of a function or of a partial function just to mean the representability of the graph of the partial function. In Rautenberg, he doesn't call any notion strong representability. Rather, he uses this as what he means for a partial function to be representable. So he uses this as the notion of representability for functions, this notion with respect to Q. But I think it's useful to have the simpler notion of just representability of the graph of a function as the basic notion of representability of functions, because that almost always is enough. And it's just in this one place in the diagonal lemma we need this stronger Q representability, and I call it Q representability because it has a property that's about provability in the theory Q. Okay, right. About the proof of this, and then we'll have a break, and then we'll in the second part we'll do the third part we'll do then finally Gödel's theorem. But essentially we're now completing the proof of the diagonal lemma. Okay, so R is a computable relation. So that means it is sigma 1 representable and its complement is sigma 1 representable. So let's have a formula B that represents R. So this can be x1 to xk and y. Be a sigma 1 formula representing R. And let's have C for complement. So let this be a sigma 1 formula representing R complement. And the idea is we want to find a sigma 1 formula that represents, again, R, but in a sufficiently nice way that we can prove this second property here, which is the stronger property that we get. The fact that Q knows that the relation is single valued, essentially. So the idea, so we would like to use the formula so we want to represent R. So we're going to use these. We're going to use the B formula because that represents R, but we're going to add a clause that kind of gives us more information. We're still going to represent the same relation, but more information that essentially forces, just through the logic, forces the, where is it? Forces M in this case to be the unique value. And we can do that by simply adding a bounded quantifier here for all Z less than Y. The point is, if it holds for Y, if this is the only value, then it will never hold for any smaller values than Y. So for all Z less than Y, the complement property will hold. Okay. So we like to use a formula like that, and it's kind of rather intuitive that you don't need very much strength of logic to go from this formula to seeing that for any fixed numbers n, numeral for n is the unique value that can be in this relation. Okay. However, we can't use this formula. Why not? This is the property. So we're going to have this as our property. It's clear it represents the same relation semantically. Okay, because we've got this single valued condition, it represents the same relation semantically. So we can use it, and if we use it, we've got more strength in the relation that makes it easier to prove in a weak theory that this property holds. But there's a reason that we can't actually use this formula. It's not sigma 1 because B is sigma 1. It's got existential quantifiers, and C is sigma 1. But we've wrapped the existential quantifiers here in a bounded universal quantifier. But we can convert it to a sigma 1 formula. So instead, let's suppose, let me just rub this off. It's in the notes anyway. Well, I would have compared it, but there isn't much space. So suppose B is let's keep it consistent with my notes up to Zm B prime, where B prime is delta 0. And suppose C exists W1 to Wm C prime, where C prime is delta 0. So we define formula A, x1 to xk y to be, so this is our representing formula, to be there exists z1 up to zm. Now we can put the b prime here, and as we had with, for all z less than y, as we had before, we want to say for all z less than y, C holds. So C exists W1 M. I seem to have M in both places in my notes, actually. Let's call it N here. So we want to put something like this in, but we now need to bound these quantifiers. So what we can just do is give ourselves a bound here. Exists a V, and we just require all these quantifiers to be bounded by V. And this works. And now we've made it sigma 1 because all the quantifiers in here are bounded. So the reason it works, it's a pity I rubbed out the formula we had before, but the formula we had before said that for all z is less than equal to y. So this is here's C of x1 to xk z instead of y. I hope that was clear before.
W1 to Wn.
Sorry, what's the question?
Does C prime really take x1 through xn, or are it supposed to be W1 to Wn?
Yeah, so C prime has x1, so I'm kind of plugging in these variables, but there are also the w's in it as well. So really, yeah, notation's not. So here we should have a b prime of x's, z's, and x's, z's, and y, and here a c prime of x's, w's, and y, and here we use the x's, the w's, and the z instead of the y.
I thought the x's came after the z's.
Well, it doesn't really matter, does it?
Yeah.
Yeah, they can. It doesn't matter the order we write the parameters. I think I've written enough on the board. I mean, I'm happy to clarify. I just don't want to make things look more horrible. And yeah, I shall think about whether the notes are written very nicely. The point is, this works because here so originally we had unbounded quantifiers here, but we've got a universal quantification, a bounded universal quantification with some unbounded existential quantifiers. Because there are only finitely many cases here, we only need finitely many different instantiations of the universal of the existential quantifiers. So there is some bound V that bounds them all. And we can just existentially quantify over that bound V at the beginning. And that way we get a sigma formula. So it's a bit hairy, and then we need to prove that actually this works. Okay, so what I've written in my notes, so by this works by property 2 holds. So it's clear that property 1 holds, 2 holds by basic lemmas about the theory Q, similar to last week. About Q. And there's a section number in the notes, which is section 6.3. So I think that's as much detail as I want to do about this. But, you know, we did a lot of faffing around with Q last week, and one needs to do more faffing around with Q in order to get this to work. But we've got still 5 minutes till the break. So this is a good point to make a confession about what I did last week, which I only became aware of today, and I'm pretty sure that, yeah, there isn't a way around it, and so this is not in the lecture notes, but I'm tempted to stop the recording as well. But anyway, so last week we defined in Q, so the relation, the less than relation we defined to be using the same formula we've been using since the beginning of the course. There exists a z such that x plus z equals y. Okay, and we proved all the results last week using this definition of the order relation. And I wanted to use this definition of the order relation because this gives the ordinals are a model of Q, and this defines the correct, for those of you who know what ordinals are, this defines the correct order relation on ordinals. However, Rautenberg, and probably everyone else in the logical literature, defines x is less than or equal to y to be there exists a z plus x equals y, which does not define the correct order on the ordinals, but you know, we're not actually studying the ordinals anyway, so it's not really neither here nor there whether we define the correct order on the ordinals. And it seems that this definition is essential for this strong Q-representability result to hold. So the correct definition of the order relation should be this, and they're not equivalent in Q because Q does not prove that that addition is commutative. Okay. So the results I proved last week, I was using this relation. One needs to redo the proofs, which can be done using this relation instead. But the reason this is correct, so for the correct less than equals, Q proves for all x, 0 is less than equal to x. Okay, I can't see that that's true for this one. Also, and more importantly, and the crucial property that's used in the last step here, a generalization of this, Q proves for all numbers m in the meta theory, Q proves for all x, either x is strictly less than, we need to have the corresponding definition of strict less than, either x is strictly less than m or m is less than equal to x. This is just the case for the case of, this is a special case of that with m equals 0. This is for all m in the meta theory. And this is used crucially in the proof of this strong Q-representability theorem. So next time I teach the course, I shall be a bit more careful about that. But I've taught the course, I've taught this many times before without ever noticing it. So it's amazing. And you know, maybe I'm missing something, but I don't think so. Yeah, are there any questions? A break until 15:15, and then the last hour will be actually getting zero. Just to begin, as Mabel pointed out in the break, so I was saying I considered the order relation in Q in the way I defined it originally, in order that the ordinals would be a model and this would be the correct order relation on the ordinals. As Mabel pointed out, actually the ordinals do not satisfy the axiom AQ that says that every x is either 0 or a successor. So the whole idea of modeling things around the ordinals was actually just very misguided in the first place. So anyway, Q should have been defined last month with the axioms as it was. I should not have ever mentioned the ordinals being a model, because they're not, at least not with their standard successor operation. And the correct thing to have done last week would have been to define the order relation in the way that I just defined it before the break. Right, okay. With that being said, we now move on to finally Gödel's incompleteness theorem. And the idea is now very easy to express. We have the diagonalization lemma. And so Gödel's idea is use the diagonalization lemma, the diagonal lemma as they called it, to construct, to find a sentence G that says basically, so the diagonal lemma says for any property of numbers we can find a sentence that says I satisfy this property, and the property we choose is the property of being unprovable. So the sentence will say I am unprovable. It says I am unprovable. And then it's going to be a contradiction for it to be provable. So therefore it won't be provable, and it will be true because it's not provable. So it will be a true sentence that is not provable. So it's a really nice idea because there are, all these kind of related paradoxes, like the liar's paradox, which is I'm not true. Those are genuinely paradoxes. Whereas here we're using something similar. It's not a paradox, but we get a very positive result because we get a true sentence that is unprovable because it says it's unprovable. But in order to be able to do this, we need to have a predicate for provability. So that's the next thing we're going to introduce, is the provability predicate. So to have a provability predicate, we're going to, hello. Hi. Just arrived in time for Gödel's first incompleteness theorem. And so might be missing a bit of background. So to have a provability predicate, we need the theory to be computably axiomatized. And so once again, when I say computably axiomatized, I mean a theory together with a computable axiomatization. What I might ask for is a primitive recursive axiomatization, just to raise that as a possibility, and then we sort of computably axiomatize in a particularly nice way. So I just want to remark before we carry on that we had the informal result for using informal computability theory a few lectures ago, where we did computably axiomatized, the notion of computably axiomatized theory, that if a theory is computably enumerably axiomatized, then it is also computably axiomatized. It turns out that you can strengthen that it can even be given a primitive recursive axiomatization. So every computably axiomatizable theory has a primitive recursive axiomatization. So we need to work with, we'll need to work with computable axiomatizations axiomatization. And in fact, every computably axiomatizable theory is primitively recursively, I'll just write prim-rec axiomatizable. So if you can find the computable axiomatization, that's a decidable set of axioms, we can even find a primitive recursive set of axioms. So the proof of that is like the proof that computably enumerably axiomatizable implies computable axiomatizable. If you do that proof formally knowing some computability theory, you can do it using clean is T predicate, which is a primitive recursive predicate, and the proof actually basically gives you a primitive recursive axiomatization. It just falls out of the proof. So in previous incarnations of this course, I've using this fact, I've then just proceeded from now on to use just primitive recursive axiomatizations. I've decided this year to try not doing that. So today, so what we're going to do today is we're going to assume we have a computable axiomatization, and I'll just make remarks about stronger things that hold if it's a primitive recursive axiomatization. Okay. Anyway, henceforth, we assume a computable axiomatization T, so a computable set of axioms for an extension of Q. The Q axioms in the axioms of T, but we're allowing some other axioms as well, and we just require them to be a computable set of axioms. Okay. So now we're going to define relations that relate properties, that express properties related to the notion of proof and provability. With a fundamental relation, I'm going to call P proof, the proof, sub T, because it depends on the theory T, depends on the axioms we've got. And it's a binary relation on numbers. And this is defined to hold if and only if n is the code of some sentence A. Oh, in fact, formula of some formula A, and P is the code of a proof of A from axioms in T. So I haven't said how we encode a proof, but a proof is just a sequence of formulas satisfying rules that each step is obtained either by using one of the axioms or by deriving a formula, either one of the axioms in T or one of the logical axioms from the Hilbert proof system, or by deriving the formula from previous formulas using one of the inference rules. And these can all be coded up by, we know how to encode formulas, so we know how to encode sequences of formulas because we know how to encode sequences. We already did that earlier. We know how to encode sequences of formulas, and there is a not too difficult algorithm to test. If you've got a computable axiomatization, there's a not too difficult algorithm to test if a sequence of formulas is a proof. That's proof checking, as a computer proof checker would do. And in fact, that procedure of proof checking is primitive recursive, subject to being able to check that the axioms in T that a formula is that a sentence is an axiom in T. And so if we start off with a primitive recursive set of axioms, then this is primitive recursive. In general, if we have a computable set of axioms, this is just computable. So this is computable, and it's prim rec if T is a prim rec axiomatization. Okay, so this is a decidable property, and that's how proof checkers work. You give the formula and the proof, and your proof checker checks that you got the proof right. Then there's the predicate, the provability predicate. This is the proof relation. Let's maybe put the provability predicate on the other board. Oh, let's put it. Then we can squeeze here. The provability predicate in inverted commas, meaning just a unary property. So this I'm going to write as prov sub T n. And we define this to be, so we can actually give a formula for this. Can anyone guess what it is?
There exists.
It's just, there exists an X. Right, such that X is a proof of Y. So this, I'm simply defining this as an abbreviation. So, sorry, this is the relation. So because it's computable, it's represented by a sigma-1 formula. In fact, it's strongly Q-represented because every proof has a unique conclusion. So it's again partial functional from the proof to the formula that's being proved. So this is a sigma-1 formula. Here we've stuck an existential quantifier in front of the sigma-1 formula, so it's also a sigma-1 formula. And now we can get Gödel's true but unprovable sentence using the diagonalization lemma. So using the diagonal lemma, we construct GT such that the diagonal lemma constructs it for us, such that GT says of itself I am not provable. So it's going to get really tedious to put all these numeral bars on, so I'm going to stop doing that for now. Okay. And this is provable in Q by the diagonal lemma, because the diagonal lemma was about provability in Q, so it's certainly provable in T as well. Okay. So this is the sentence that says, I am not provable. And now we can state Gödel's theorem. Gödel's first incompleteness theorem. So suppose T is a computably axiomatized extension of Q, but I won't write that because that's our running assumption. Then, three properties hold. Firstly, the Gödel sentence is not provable. Secondly, as long as T is one consistent, so it only proves true sigma 1 sentences, T is one consistent, then the negation of Gödel's theorem in which the assumption of one consistency is dropped. I've already mentioned that. But for this version, when we use the sentence of GT, where we use the sentence GT that says, I am not provable with this formula, one consistency is necessary. So in order to drop one consistency as an assumption, you need to change the formula GT. Okay, for the formula we're doing, one consistency is needed, but that's okay because we want our axiomatic theories to only prove true sentences of arithmetic, and this is only requiring them to be true on sigma 1 sentences. So it's weaker than requiring that they only prove true sentences. And finally, the theory, so these two give us incompleteness in the sense that there is a sentence such that neither it nor its negation are provable. But finally, the sentence GT itself is true. So we've identified a true sentence GT that is not provable. The third property is that in the model of the natural numbers, GT is true. Okay, so we just need to prove these three statements, and then that's going to be it for today. And these proofs are all relatively quick and nice little arguments.
So we needed self-referentiality critically for constructing this GT.
Yeah, well, the diagonal lemma allows us for any formula to say, produce a sentence that says, I satisfy this formula. Then we need the Gödel numbering of proofs in order to state the property of not being provable. And then we want the sentence, I am not provable. Yeah, so then the diagonal lemma gives us that. Yeah. And in general, the diagonal lemma gives us a way of constructing self-referential sentences that say of themselves they satisfy whatever specified property, A, as we called it, in the diagonal lemma, and whatever property is specified to begin with. Okay, anyway, let's prove these three properties. So the first one, so we want to prove that GT is not provable. So suppose the contradiction that the Gödel sentence G is provable, then let's call this property star, the diagonal property. So then T proves that T proves the negation of the sentence in arithmetic that states that GT is provable. But GT is provable in T by the assumption here in T. So, but the statement that GT is provable that GT is provable, the formal statement is true, and this is a sigma 1 sentence. So by one completeness, T proves that. And this contradicts consistency of T, which is part of the running assumption that I didn't write. But actually, let's make it. But actually, if T is consistent, let's put it like that, then T does not prove the Gödel sentence. Okay. So here we've got these two. We have both a sentence and its negation, so this contradicts consistency. Okay, so that's statement 1. Statement 2. Suppose T is one consistent. Let's not write that down. So suppose we want to show that T does not prove the negation of itself, that T does not prove the negation of the Gödel sentence. So suppose it does prove the negation. So by star, by the diagonal property, T proves the sentence that formally states that GT is provable. But again, this is a sigma 1 sentence, it's provable, and by one consistency, it's true. So by one consistency, that's true in the natural numbers. Hence, that T proves the Gödel sentence, because that's what provability means. And now we've again got a contradiction with consistency. So again, which is, if we're one consistent, then we're a fortiori consistent. Again, we contradict consistency. But the idea behind these two is very straightforward, because G says I am not provable, therefore it can't be provable, because if it were provable, we would be proving, I mean, it's basically, if it were provable, we would be proving something false. I mean, it's a bit more subtle than that, but
Excuse me.
Yeah.
I have 2 questions. Here you said that we contradict consistency,
yeah.
but we only assume one consistency.
Yeah, but one consistency is a stronger assumption than
We
consistency.
always, okay. I
Yeah.
don't.
We've used both one consistency and consistency. Okay, and property 3 is, well, we have that by the definition of the provability relation, for any sentence A is provable if and only if the formal representation of provability is true in the natural numbers if and only if A is provable, because that's exactly what the provability relation is supposed, the provability predicate is supposed to say. So by 1, So again, we need consistency here. So consistency should just be a global assumption. By one, then we have, because T does not prove GT, well, that means that N does not hold in N, but GT is provable. This was for all sentences A. So specifically for the Gödel sentence, it's not true in the natural numbers, but the provability relation. So by star, if this is true in Q, it's true in the natural numbers. So GT, sorry, the negation of GT is not true in the natural numbers. So the Gödel sentence is true in the natural numbers. Okay, and we're done. So this is Gödel's proof of incompleteness. This clever sentence that says, I am unprovable, turns out to not be provable, it can't be provable. As long under a mild assumption, its negation is not provable either, so we have incompleteness, and moreover, the sentence is true. Because provability is a sigma 1 sentence, this is equivalent to a negation of a sigma 1. So GT can be expressed by a sequence of universal quantifiers followed by bounded quantifiers. It's what's called a pi 1 sentence. And we therefore found a sentence of a very simple kind. It's just universal quantifications over numbers. And in fact, you can even make that a single quantification over numbers followed by the decidable property. And it's true for every number, but we cannot prove that in the theorem T. Okay, are there any questions on that?
Just intuitively, it seems more awkward that this is actually true in the natural numbers compared to it's being unprovable.
Well, it's true because it's unprovable. Because it says I'm unprovable, and then it's true. So we have to. So okay, that is a good point. So there's another argument for why it's true, which is just that it is a pi. It is an unprovable pi 1 sentence whose negation is also unprovable. So if you have a pi 1 sentence whose negation is unprovable, then it's automatically true. Sentence whose negation is unprovable, it's automatically true, and that's because T is sigma 1 complete. Argument. So there's actually, once you've got 1 and 2, there's a nice argument for 3 holding that does not actually use anything about the meaning of G itself. Just the pure syntactic form of G is enough. Yeah, good. That's everything for this week. Yeah, so next week we have Gödel's second incompleteness theorem. And there are only 2, so there won't be a third incompleteness theorem afterwards.